thank you for joining today's webinar, which is part of the ongoing series hosted by the CELLAR project. Today's focus is on the AI services offered by the project and how energy communities and other users can benefit from them. To begin, we will provide a brief introduction to the CELLAR project for those who may not be familiar with it. And following that, we will have the main presentation from Sara De Luca from Links Foundation, the partner responsible for developing the services of the project. And finally, we'll wrap up with a Q&A session, so feel free to note down any questions you might have during the presentation. So thank you again for joining, and let's get started. So I will start with some general information about the project. The project has duration of 42 months, has 31 partners, 9 million euro budget, and it started in June 2022, so we're close finishing up. And it also has 9 validation cases, which I will talk a bit more on later on. So 31 partners from 15 countries around Europe. The consortium is multidisciplinary and complementary, which is needed to achieve the objectives set out from the project. So what are our objectives? To empower citizens in participating in the energy transition, promote energy data exchange, moving from decentralized data valorization, and also creating value from energy data. Maintain the control of the data of the level of the data provider, which is an essential data space principle. And finally, the project aims to promote interoperability by following and advancing existing standards and practices. So how we aim to reach our objective through CELLAR. CELLAR aims to create an energy data space that will support the creation, development, and management of energy communities, a concept that the EU has put in the center of its energy transition strategy. And this includes the development, validation, and demonstration of a dynamic data hub, the implementation of privacy and cybersecurity by design principles, delivering data-driven energy services to support the energy transition, create a DLT-based open marketplace, evaluating novel business models, collaborating with other EU relevant initiatives, and also have 9 validation cases. The validation cases are a very important part of the development process of CELLAR and its components, to ensure that we are developing something that energy communities and targeted, let's say, users will actually use. To ensure a holistic approach and to account for different interpretations of the energy community concept, we have energy communities from different countries with different levels of maturity, different configurations, and different activities. Here you can see the 7 validation cases that are actually energy communities, as I mentioned, different sizes, different activities. And also we have 2 data providers, which will help consume data and populate the data into the platform. Here you can see potential beneficiaries or users from CELLAR, which Since the availability of energy data is essential nowadays, it can help different stakeholders related to energy communities or beyond energy communities. On your right, you can see the services and tools that CELLAR has to offer. So a very high, let's say, illustration. In the last webinar, we had a look in the dashboard of the project. So today we're moving to the AI services provided through the project. So thank you for listening. I will now leave the floor to Sarah to begin her presentation on the dashboard. So I will stop sharing. Sarah, you have the floor.
Good morning, everyone. Thank you, Georgios. So let me introduce myself. I'm Sarah from Links Foundation, which is a partner of the CELLAR project. I've been working in the task of developing AI services, AI-based services for the energy communities of the CELLAR project. And today I will present you some general concepts about AI in the energy sector, and we will see a little bit more in detail the services that we developed for the CELLAR project. So let me share the screen. Okay. So we all heard about AI lately. So when we usually think about AI, it comes into mind first the chatbots. However, AI can be useful for a wide variety of things. For example, it could be very useful in the energy sector to predict patterns, detect anomalies in the energy series. For example, to provide insights, recommendation, and help in the management of an energy community. This could lead to reduced cost, better management of renewable resources, and thus enhancing the sustainability. So how does it work to train an AI model? So first of all, we need to have a lot of data. Probably we usually need hundreds of thousands of samples. We start by having input data and what we know that is the solution to the problem that we define. So the expected output that we want from our network. So we start by having our data and the solution. First thing that we do is take our data and give it as input to a randomly initialized model. The model will make a first prediction, which will probably random and not accurate, and will output these results, first random prediction. Then what we do is defining a loss function. What is a loss function? A loss function is a measurement of the error between the predicted output and the expected output that we know being the true value. So we measure the difference between what we predicted and what we expect. Once we know this error metric, we do an operation that allows AI to learn, which is called backpropagation. So we return the information about how wrong was the prediction to the model, which will update their internal parameters to try to tune the prediction towards the expected output. And this process is repeat many times until the predicted output is acceptable to us. And in the end, we can say that the model is trained. So what do we do as developers? First of all, we study the data. We need to clean the data, understand which ones we can use and which one we need to discard. We need to define a specific task that we want to train the AI on. Then we choose the appropriate model given the data that we have and given the task that we need to perform. Finally, another important step is the selection of the loss function. So which error is best for the task that we chose, which error metrics to use. And finally, we do the training process that I just showed you. We evaluate the model, and finally, after evaluation, we always go back to the data because we probably are not satisfied with the outcome of the model we just trained. So we either change the preprocessing of data or choose another model. So everything starts and ends with data. So how does it work to use an AI service in DataCellar? A user that has their own data connects to the dashboard through the connector, which is the component in DataCellar that allows the user to connect to the data space. Then we created this component, which is called the deployment platform, which dispatches the request of the user by taking the input data of the user and understanding which model needs to be called based on the user request. First, before giving the output, the deployment platform retrieves weather data, which are needed to generate the prediction, but we will see this in a bit. Chooses the selected AI model that can generate the output, and then finally returns the output to the dashboard that is finally displayed to the user. In developing these AI services, we always had in mind what could be useful to the local energy communities that are participating in the DataCellar project. And here is a list of what we developed and why it could be useful. So the first thing that we implement is the forecasting. So forecasting means just predicting the output of a PV panel or a wind turbine, so of renewable energies that are present in our local energy communities. We give the user the possibility to have a short-term or a long-term forecast. The only thing that the user is required to have in order to generate forecast output is the past production from their PV panels or wind turbine. So by having enough history of their production, usually we're talking about 120 hours, so a few days, we can generate a forecast of the prediction of the production. Why this could be useful? Because it could enable the adjustment of the grid management and of the storage of this energy. It can maximize the efficiency in the energy production and support the integration of the renewable energy into the energy mix. How does it work? So as I said, the user needs to have needs to provide two things: the history of their past production, either PV or wind turbine, and their postal code. Why do we need their location? Because this prediction, this forecast model is highly dependent on weather data. Therefore, we need to retrieve from OpenMeteo, which is a weather forecast service. We need to retrieve the weather forecast and the associated weather to the historical production in order to study the relationship. The model needs to study the relationship between the production and the weather, and given the forecasted weather, it will give a forecast on the production. The same concept applies to another service, which is the energy consumption forecast. So given a historical consumption inside a household, the model can generate either short-term or long-term forecast of the energy consumption inside the house. This can be useful to manage the energy in a more efficient way inside the house. It would be useful to predict peak times. Can be useful if someone has production and consumption inside the same building. It can be used to balance between consumption and production. Also here, it works just the same as for the forecast of the production. We have a time series, which is the historical consumption of the user, and a postal code. Also here, we need the location, we can say approximate location of the data where we want to generate the prediction, because the model needs to also here retrieve weather, historical weather measurements and weather forecast. The output looks like this. We have the input data, which is the purple line that you can see in this example, and the predicted outcome, which is the dashed yellow line. Another application that we have is the anomaly detection. So the anomaly detection is the task of identifying unusual patterns or deviations from the usual trends in a time series. We can apply this to both production data and consumption data. Also here, the only thing required by the user is to have some history, so a few days of history of production or consumption data. This can be really useful for maintaining the operation of the system, trying to predict when downtime can happen based on anomalous patterns that we could find, and it can enhance the lifespan of the appliances in the household or of the PV panels and the wind turbines. So how does it work in practice, the anomaly detection? We always have the past data given by the user. The first thing that the model does is use the forecast model that I just presented to generate a forecast. The difference with respect to before is that the anomaly detection calculates the difference between the forecasted time series, the forecasted values of anomaly, consumption or production. So it calculates the difference between the predicted values and the actual values. So if we predict 1 hour ahead, we compare in the next hour the predicted value with the actual value that we measure in that hour. This leads to a computation of a difference on which we apply a threshold, and if the difference between the predicted and the true value is above the threshold that the model defines, then we consider that point an anomaly and we raise an alert to the user. Another interesting application is the NILM, which stands for non-intrusive load monitoring. So what does it do, this task? It takes the aggregated consumption of the household, so the total consumption of the house, and it learns to disaggregate this time series into multiple time series that represent the single consumption of each appliance. This application can be really useful because it can delete the need for direct sample installation on each appliance if we want to know, for example, the disaggregated consumption of the fridge, the washing machine, etc. So just given the aggregated consumption of the household, it will output the disaggregated consumption of each appliance. Also here, the only thing required by the user is to provide a few days of the time series of their energy consumption. How does it work? We have, as I said, the aggregated load, so the time series of the power consumed inside the house. And then we train one model for each appliance where we want to predict the disaggregated load. So for example, if we want to know the disaggregated load of the fridge, we call the NILM for fridge model. If we want to know the disaggregated load for the dishwasher, we call the NILM for dishwasher, and so on for each appliance of the house. So there was a different training for each of these appliances. Last application is the battery optimizer. So the battery optimizer is the task of predicting, let's say, rather than predicting, recommending a profile for the battery state of charge. So suggesting to the user when to buy and when to sell the energy in order to optimize either the cost or the efficiency of the battery storage. What it requires the user to have both a consumption and a production profile, and it can be really useful for the management of the battery charge and the optimization of the selling and buying time, since the decisions are also based on the price of the energy. So let's see more in depth how it works. So first of all, in the first time series that you can see here, we have the energy prices. This time series is retrieved automatically by the user from official sources. So the first input to the model is the energy price. Then we require the time series of production and consumption, which needs to be provided by the user because it's, of course, highly personalized. And what is the output of this model? So the output is these three boxes that you can see here. First of all, we have the battery operations. So when to charge and when to discharge the battery. Dependently, of course, on this battery operation, we have the information of when to do the grid exchanges. So when to sell, when it's convenient to sell, and when it's convenient to buy. And finally, these outputs are, of course, all dependent between one another. The final output is the battery state of charge. Then, inside the data CELLAR project, we also implemented this tool, which is called the Orange Data Mining tool, which allows the user to build their own AI service based on the data that we have. So if a user, for example, has a little bit of key concepts about how to process data and how to which operations to perform to train an AI, but does not have, for example, coding skills or does not want to does not have the resources to train an AI model, it can use this Orange Data Mining tool. How does it work? It's an interface with the widgets. So each widget is an operation to perform on the data. For example, we have the transform of the data, which are just select, for example, select a row, transpose the matrix, I don't know, input missing data. We have the visualization, and then we have a wide selection of models that we want to choose, that the user could choose. For example, simple regression or also more complex unsupervised models. Let's see an example of how this tool works. So it's a drag and drop interface, meaning that from the widgets panel, a user can select the operation they want to perform and drag it on a blank space where they can connect and stack series of operations to perform the data. Let's see an example. The user has their datasets stored in a CSV file. The CSV file looks like this. It has columns and rows with the rows representing the date time and the columns representing the features of the data. First, we apply a pre-processing step. So a data filtering to remove, for example, missing data or aggregate or disaggregate the timestamps. And then we perform feature selection. So we select only the columns that we want to use in the model. Then here in this example, we applied a random forest, which is a very simple AI model to perform prediction, to perform forecast. So the user can drag and drop the widget for the random forest, connect it to the training, to the previous preprocessing step, and start the training process. The training process will output graph about the loss, so how the model is learning. And finally, we have the chance to save the model inside the data CELLAR platform and sell it on the marketplace, share it with other users to make it available to all the other energy communities. So before ending the presentation, I just wanted to show you an example of how our dashboard looks like and how the interface of our AI models usage works. So this is the data CELLAR dashboard. It's currently not public yet, but it will be very soon. We have here on the left panels about, for example, the first thing that we see is the dataset. So we can see which dataset we own, which one we uploaded on the data space, which dataset we purchased from the marketplace. So for example, let's suppose we own these consumption and production data from several buildings. We want to do an application of, for example, we want to disaggregate the loads and know for each building the disaggregated load of each appliance. So we go to standard AI models, which are the AI models pre-trained by us that we make available for every user in the CELLAR platform. And we select the task that we want to perform, in this case, non-intrusive load monitoring. The first thing that we need to do is select on which dataset we want to perform the disaggregation. Let's try with the first building that we have. We just click Run, and the dashboard will output for example, the disaggregated load of the fridge, the disaggregated load of the washing machine, and the one of the dishwasher. This also applies to other all the other models that I just presented, and this will be available for the users of CELLAR. So with this last example, I conclude my presentation. Thank you everyone for your attention, and I'm open to question answering time.
Thank you, Sarah. Do we have any questions for Sarah? I don't see anything on the chat. So if you have a question, please unmute yourself or put in the chat. I don't see any questions. We have one from Umberto.
Hi, can you hear me?
Yes.
Yes.
Good morning, and thank you, Sarah, for your presentation. It was very clear. I just have a quick doubt on behalf of the prediction. How can you guarantee that the future prediction is aligned with what can possibly happen with a given data set, for instance, energy consumption, since you use only past the data to create the model that predict the consumption for the future? What are the metrics that you normally use to do that?
Thank you for this question. To answer this question, we have an entire task built on this. We have the explainability task. So there will be on the dashboard an info box beside every output. There will be an info box containing all the information that are required by the user to understand how accurate the prediction is and how reliable it is. For example, to answer your question about which prediction metrics we use, for example, one very common, you can, Alexandra says that I can already show this for Nilma. I will try. Let me try. So as I was saying, for example, a very common metric could be, here it is. There is an info box here that tells which metrics are we using to evaluate the accuracy of the model. it also explains in depth how the model works and what it requires to function, all the explainability that a user might require. For example, for consumption, we can say that one of the most common metrics is the mean square error, at least the one that we use to evaluate our models. The mean square error is simply a difference between the predicted and the actual values elevated to the square and then performing square root. It's a very common metric. Maybe I can show you also the explainability box of the prediction of the consumption. Here it is. We have the overview of the model, the sources that we use to train the models, which types of decisions are made with the data. Then we should have model performance section. Here it is, where the user can find how reliable is the model about the predictions. This is, for example, a graph that shows how the error grows with respect when we predict 1 or 2 timestamps ahead. So on the x-axis here, we have the forecast horizon, while on the y-axis we have the mean square error. These are 2 error metrics. So, for example, if we predict 1, 2, or 3 steps ahead, we have a lower error, while if we grow the prediction horizon, of course, the error tends to grow. And so here the user can find all the information about the reliability and explainability. I hope this answers your question.
Yes, answered. Thank you very much. And that's it. Thank you.
We can close today's webinar, but before we leave, I wanted to show the upcoming webinars of the project. So we'll have a break in August, then we'll continue in September with 2 webinars, 2 crucial components of data CELLAR as well, very core components: the decision support system and the data CELLAR marketplace. So you can register for these webinars and keep an eye on the social media of the project and the website, where you can find more information. So thank you again all for joining. Have a great rest of the day.